As a lecture. The next speaker is Diego Marcon Farias. He's from the Federal University of Rio Grande do Sul. Diego was my student in some course here in the summer of so many years. And today Diego is going to talk about on the blow-up criterion of MHD equation in homogeneous Sobolev spaces.
Thank you. So first of all, I thank the organizers of the session for inviting me to give a talk here. And so I'll be talking about a blow-up criterion that we proved with a few collaborators. So this is a joint work with Melo from Sergipe and Schutz. She's a colleague in Porto Alegre, and Zibel from Rio Grande. And so the outline of the talk is going to be this. I'll be talking a little bit about Navier-Stokes equations. So first, Navier-Stokes equations. And then I'll state a few results for this system of equations. And then I'll introduce what I mean by H.S, the homogeneous Sobolev space in the whole space R3. And then I'll talk about MHD, Magneto Hydrodynamics, and more specifically about our result in this direction. So, okay, so Magneto Hydrodynamics is basically, I want to study the velocity of a fluid together with a magnetic field. And so the velocity is governed by a Navier-Stokes equations, which is coupled in a simple way with Maxwell's equations of Magneto of Magneto hydrodynamics, sort of. So okay, so the Navier-Stokes systems. Navier-Stokes is as follows. I have ut plus u dot grad u plus the gradient of the pressure is equal to Laplace of u. And here I'm looking in the whole space in R3. So this is in 0, infinity, cross R3. And well, also here I'm considering incompressible Navier-Stokes, so I have the divergence of u is 0, and I assume that also the initial condition u naught is divergence free. Okay, so this is the Navier-Stokes system. This I call it a system because it's a vector equation. So u is u1 of xt, u2 of xt, u3 of xt. Okay. So the most basic question for this equation is, are there smooth solutions? This is still an open problem. It's a very famous open problem. To prove that in 0 plus infinity, we have classical solutions to this system. Yeah, so this is a very famous open problem. This is unknown, and yeah, some people might say, so you get $1 million, right, if you solve this. And some people might say this is the hardest way ever to get this 1 million. And then, okay, but the partial results are known. There's this famous theorem that goes back to the 30s by Lihe. I don't know how to pronounce, 34. And this ensures the existence of a maximal time T star, which depends on the initial condition here. And so this, what's unknown up here is that is T finite or infinite? This is unknown, so this could be finite, or let me put it this way. Or infinite. And such that Navier-Stokes admits a solution, a classical solution. Well, maybe to be more precise, I could just put T star here, and then here is a T and T here. So the system admits a solution when for some T star, which is positive. All right, so a blow-up criteria is also known for a long time for this kind of equations. For instance, a simple one, which goes back to Leray as well, is that if we assume that T star is finite, then we have a blow-up of the L infinity norm. So the supremum for T in between 0 and T star of U L infinity is plus infinity. Or even a little bit more precisely, we can say that the lim as T grows to T star of the L infinity norm this is R3, right? Is plus infinity. So this is also known of Lihe. Okay, in particular, this shows that if one can prove that there exists a positive T for which the solution is uniformly bounded in this interval, then you can push T a little bit. You can find a bigger T for which a classical solution exists. And then if you suppose that T is finite and is the maximal one, it's not possible because you could push a little bit longer from the boundedness of the L infinity norm. So that's why this is a blow-up criteria. Either T is finite and we have blow-up of the L infinity norm, or the norm is bounded and we have a classical solution for all T positive. So a second criterion would be for the gradient. So if we suppose that Q is between 3 halves and plus infinity, and T star is finite, then the gradient norm in LQ also blows up. So this is the soup T star. All right, so all this is very classical, but for homogeneous, so now here this is like H1Q norm somehow, and for homogeneous Sobolev spaces, very recently has been some advance in this. Well, very recently, Ben-Amer obtained a different blow-up criterion, and then I'm going to show what it is. So homogeneous Sobolev spaces. These are defined as H dot S of R3 as the set of tempered distributions U in R3 for which U is L1 lock and the integral in R3 of psi to the 2s U hat square d psi is finite. So here, as usual, the U hat is the Fourier transform of U. And then we know that the homogeneous Sobolev space is a Hilbert space if and only if S is smaller than 3/2. So here, more generally, it could be D over 2. The dimension is 3 in our case, so 3/2. All right, and but anyways, the inner product is well defined, even though the space is not complete for different values of S. So anyway, we can define the inner product as UV to be the integral in R3. So this is an HS of psi to the 2s U hat dot V hat. And here is no. And then, well, actually here I'm considering vector valued functions. So this is the complex inner product. This is U hat dot V hat is actually UI hat times VI hat conjugate. So if we're in one dimension, here we have directly, that's why I got confused a bit. All right. Then for these spaces, we have an interpolation inequality. You can't really compare two of them by just, if S1 is smaller than S2, you don't know which one's contained. There might not be a relation, a direct relation, but you find an interpolation result like this. So if you have that S is in between S0 and S1, and then you write S as a convex combination of these two, plus theta S1, we have that the norm of U in HS is less than or equal to the norm of U HS0 to the 1 minus theta times U S1 to the theta. And then this is basically what Ben-Amer used in his paper 2010. 2010, to obtain a different sort of blow-up criterion for Navier-Stokes equations. So he assumes you have a solution. Well, you can always assume there's a classical solution in the maximal interval, but then you have also a solution in this space, Hs of R3, with S bigger than 5 halves. So this is a maximal solution, or T star is the maximal value, so I say that U is a maximal solution. So U, in this case, is a maximal solution, or is a solution of NS T star. So if T star is finite, then he gets two different criteria. A is norm of U for fixed T in L2 is times UT HS dot is greater than or equal to C that depends only on S over T star minus T to the S over 4. So here, this exponent is positive, so you get a quantitative way of seeing how these norms are blowing up. So once T approaches T star, we get here, this is blowing up, so we get a quantitative inequality. And the second one, similar. So if T is finite, Benamer could show that UT in L2 to the power 2S over 3 minus 1 in H dot S is greater than C of S to the T star S thirds. Okay, so the idea of our work came up in a discussion with a colleague in Porto Alegre. And we had this idea of trying to interpolate these two into only one inequality with a sort of parameter that could go, from one to the other with a more general inequality, and while keeping this as like the same results, but with a parameter running from 0 to 1, let's say. So we did that. That was our project. And plus, we showed that you can even consider a more general equation when doing so. So now I introduce the Magneto Hydrodynamics equations and show more or less how to obtain this sort of blow-up criteria for MHD. Okay, so MHD stands for Magneto Hydrodynamics. And the system consists basically of a Navier-Stokes equation for the fluid velocity. So UT plus U dot nabla equal Laplace U plus. So this is how the magnetic field is coupled into the equation. Well, here I could have a minus sign. So this is the Navier-Stokes equation that incorporates this magnetic field that is acting on the fluid. And then the evolution equation for B is given in a similar fashion. Like this is equal to Laplacian of B plus well, and here we also consider incompressible equations. So we have the divergence of U is always 0. So this models incompressibility. And it's also natural to assume that the divergence of B is equal to 0 in accordance with Maxwell's equations, because here we assume there are no magnetic monopoles. Or that magnetic charges do not exist. And the initial conditions are also, we also suppose they're divergence free. So we have U of x at 0 is equal to U naught of x, and B of x at 0 is B naught of x. And divergence of U naught is 0, divergence of B naught is 0. Okay. All right, so many people actually worked on this kind of system, and then I'll cite a few names that have proved existence of solutions in the same sense of Navier-Stokes equations. So they proved the existence of a maximal time t for which classical solutions exist. And well, that's the best you can expect, right? Because if you set B equal to 0, this is precisely Navier-Stokes, and then you would have $1 million if you showed that this equation has a classical solution for all t's. So this is a large list of people. Clapper. Well, I'll cite some of them. I'm sorry if I forget important contributions. Sermon. Damon. Yuan. So these people extend many of the results that hold for Navier-Stokes for this kind of system. So in particular, the existence of this of classical solutions for some t positive. They also show the celebrated Caffarelli-Kohn-Nirenberg for this kind of system that the Hausdorff measure of the singular set is 0. And then, okay, so our result is the following. So this, as I said at the beginning, this is a joint work with Melo from Sergipe and Schutz and Zibel from Rio Grande do Sul. And we prove that if S is greater than 3/2, and we have initial conditions in the right space for us, which is H dot S naught, and U a solution as in Benamer C of 0 T star HS. So a solution of MHD. So if the maximal time, so T star always denotes the maximal time for which you have classical solutions, okay? So if this maximal time is finite, then you obtain a blow-up criterion, as I mentioned before, that sort of interpolates between those two of Ben-Amer. So we get that. Then let me continue here. For all parameter between 0 and 1, we consider S to be greater than or equal to 1/2 plus delta and so we have that the joint norm of U and B, which by the way is just taken to be we just consider U squared plus B squared in HS. So we just kind of consider the Euclidean norm that and this happens to be the same as the homogeneous Sobolev norm for 6 dimensions. So this is just a simpler expression for it. So this times the L2 norm of UB to the power 2s over 1 plus 2 delta minus 1 is greater than CS delta over T star minus T to the power S delta over 1 plus 2 delta. Yeah, so this is the result that we get. Well, we can get a few other inequalities, but this is the main theorem. And so a few remarks about this exponent will show that that's a particular case of this. So remarks number 1, well, is that if B is equal to 0, if B is identically 0, MHD becomes Navier-Stokes and so the choice, and then actually we have a more general, S is only greater than 3/2, while Ben-Amer had an exponent bigger than 5/2. So we can extend a little bit this exponent. S here could be taken over a larger set somehow. And then a second remark is if we set delta equal to 1/2, we get exactly A there, which is, so to obtain UB to the S minus 1, right? You put 1/2 here, and then this cancels, and you get S minus 1. And this is greater than C of S this now is fixed, right? So we don't have any dependence. And here you get 1/2 over 2. So you get S over 4, which is the same sort of inequality. So number 3, well, now this is sort of an interpolation of those two, because we can't, so to get this, we really should put delta equal to 1, and our proof is not allowing delta to be equal to 1, is only strictly smaller. So formally, if we can formally, well, we always can do stuff formally, so formally we let delta go to 1 to obtain this, right, with U and B here, now in the Magneto Hydrodynamics case. So yeah, if delta is 1, this is 2S over 3, and then here you have S over 3, which is the exact same. Yeah, so, but this is, we're not allowed to do that. This constant here depends on delta and might blow up, or it might go to 0 when we let delta to 1. So this constant might go to 0, so this is not really proved, but we have an independent argument to show that this holds. So we kind of holds in the same way as Benamer. Right. So fourth remark is actually by Professor Zingano in Porto Alegre, that his remark shows that if in our case we can set S, well, we can set S equal to 3 halves, and this is again sort of a formally, because if, oh no, sorry, that's, oh yeah, that's not formal. Yeah, S has to be greater than something, and 3 halves is included there. Okay, so we set S equal to 3 halves, and we consider this parameter epsilon between 0 and 1/2, and delta to be S minus 3 epsilon, S plus 6 epsilon. Then this implies we just plug everything into that inequality and let epsilon go to 0 at the end to obtain that the L2 norm, the norm in H 3 halves is bounded C over T minus T to the 1/2. So we would like to have that. This is actually a conjecture, even for the Navier-Stokes case. But here we have the same sort of problem, because when we let epsilon go to 0, this constant here is going to 0. And then we lose this. So here is a formal step. When we let epsilon go to 0, our estimate is just breaking up. This constant C is going to 0, so we knew that this was positive. It's nothing, but we almost get this. And this is something we don't have an alternative argument for. So this almost shows this conjecture formally. Yeah, then. So just a few words about the idea of proof. So the nice thing is that actually those are sort of elementary proofs. We can use once an interpolation inequality, which is let's say the fancier tool we use, and then we just keep track of constants by Young's inequality and Cauchy-Schwarz. So the idea of proof is to use this lemma by Schemming, which says that basically I get, for the product of two functions, remember we're considering classical solutions, so the product is well defined, and we get bound S. And then S is related to these eta and eta prime by the following. Eta is 1/2 plus a positive delta, which is that one, and eta prime is equal to S plus 1 minus delta, which is assumed, so this is the assumption. The assumption is that S satisfies this inequality here. So this S that shows up here is the one from the theorem. So we will apply this sort of inequality to S. So this, actually it's a version of this lemma. So this is the fancier tool that we use. And then the rest of the proof is sort of long but basic and elementary inequalities. Okay, so take, for instance, the first equation. Well, here there was let me just Q, it's the pressure plus that magnetic term, B. This is not going to be really. And then we just take the inner product in HS, in the homogeneous Sobolev space. Here we get the inner product with U. So we have UTU in HS plus this plus QU equal to Laplacian U, inner product U, plus this last term B. So what we do here is, these are all HS. So here we can identify this with the derivative. This is the 1/2 the derivative in T of UHS squared. And then here we can just play with symbols to get that this is U tensor U. Actually, we will use integration by parts here. To get this term. And actually, this is the only place where we use that U is divergence free. So we have, since U is divergence free, we know that this is actually equal to the divergence of U tensor U. So here is where we use that divergence of U is 0. And then by integration by parts, we can get this term with a minus sign. So here we integrate by parts and we get 0 because, so actually this step is the only one where I used the divergence is 0. Here we get 0 again, and here we get minus norm of gradient U HS squared plus B tensor B times the gradient U. Okay, then we just rewrite this. And then we use Cauchy-Schwarz to get, so these terms are both in the same side. And we have, well, here was a minus sign. So we have U tensor U minus B tensor B and gradient U. So to estimate this guy is where the lemma is coming into. And then after that, we can kind of manipulate this term to put it together with this one. And then we get an estimate by just using simple and elementary inequalities. So the rest follows. Well, it's long, but this is the beginning, and it's the basic idea. We can use this and then estimate with the right exponents. So delta also is showing up in the lemma, right? So this is where we get the interpolation. So the rest is Young's inequality and Cauchy-Schwarz. It becomes elementary after this step. And Grunwald. Yeah, so this is the idea of proof. And, well, we also get different sorts of inequalities for Fourier transforms of this solution UB. But this is basically what I wanted to talk about. Thank you.